Let's think about a process, an isochoric process, which is a constant volume one, on a closed system of a perfect gas. So this would be heating or cooling. So here's my process. This is my condition, and I'm going from an equilibrium state 1, or an initial state, to a final, or state 2, also in equilibrium. And I can use the physical properties of N, temperature, pressure, volume in each of these. Because it's constant volume, V2 is equal to V1, or delta V is 0. And because it's a closed system, then N is constant during this process as well. So for the process, I can think about what is the value of Q, what is the work, what's the change in internal energy, and what's the change in enthalpy. So this is something that we should be able to do, come up with formulas for this. Ultimately, in a numerical question, come up with a solution. But without doing a specific example, let's just think in this tutorial about how we would do something like this, given information. So a good place to start, and actually what's not written here, is other things that we might be asked for. So let me make another little column, and that might be to calculate any one of the initial or final temperature, pressure, or volume. And also included in that would be a delta T, or a delta P, or a delta V. So there's lots of things that we could be asked for. And on that note, I want to just start there. If we had any 3 of these properties, we could use PVNRT to get the 4th, because this is a perfect gas. And the same thing would occur or be true for the second state here. And because this is a change of state, I'll just do this so that I'm writing it right close to the given. I know that if PV is equal to nRT, then P1 V1 over NT1 is equal to the constant R, and that's the same for state 2, and so that is equal to P2 V2 over NT2. And so I can make use of this relationship in this change of state, because it's a constant volume heating or cooling. I wouldn't be able to make use of this relationship here if it were an adiabatic change, but this is an isochoric heating or cooling. And so if I were to find any one of these variables, I would just rearrange this equation. So I would take the R out so that this is equal to this. Right away I know this is a closed system, so my number of moles are constant. And because it's an isochoric system, or a constant volume, I know that V1 is equal to V2. So I'm just left simply with P1 over T1 is equal to P2 over T2. So maybe I want to know what P2 is, and I would isolate for that. Maybe I want to know what the second temperature is, that sort of thing. So this becomes my working formula to find either temperature or pressure. And if I know one and I'm asked to find the other, that would lead me to a delta T or a delta P as well. Okay, so now let's change gears a bit and think about what heat and work and changes in internal energy and enthalpy would be for this sort of situation, for this change. So first law always applies, so du is equal to dq plus dw. When it's constant volume, some of you might be thinking right away, well, if it's constant volume, then I can't do any work because there's no expansion or compression if the volume is constant. And you would be right. So just remember that du, while it's equal to dq plus dw, dw is equal to a minus p dv. And in this case, dv is equal to 0, therefore PdV, or specifically a minus PdV because that's what work is also equal to 0. So my work is 0 for this constant volume process. That leaves me with internal energy being equal to the heat exchange between the system and the surroundings. But it's not just any path, it's the heat associated with the constant volume. Right, so while these are equal to each other, what is the formula to determine what their value is? Well, remember the general case for dq. dq by dt is equal to c. Therefore, a dq is equal to a c dt, which is a nice relationship, but not quite a plug-into formula. Here, I have a dq sub v, and of course that is equal to my change in internal energy. And that is equal to then, I'd use a molar heat capacity, so joule per K per mole, and I must multiply by the amount of substance in moles, and then I have a dt. And so the integral of this, I will pull out what is constant. And so we've seen examples where the heat capacity is not constant, but rather depends on temperature. So you know what to do there. But let's do the easy one here where N and CV molar are constant. And so quite simply then, the heat flow at constant volume is equal to the change in internal energy, and that is equal to N CV molar delta T. So I have the expression for both Q and delta U. So just check back here. I wanted to look for Q, work, internal energy, and enthalpy. So I'm well on the way. Lastly, I have enthalpy, and I'm going to start with H is equal to U plus PV. Great place to start. It's true all the time. And now I'm going to go right to a finite change. Delta H is then going to be equal to delta U plus the delta of the PV. What is the change in the product? PV. So I could go back up here. I'm looking for the change in the product P1V1 to P2V2. So I can't keep everything in view, so let's go back here. Remember, this is a perfect gas, so I can make substitutions. But it is a constant volume process. So let's just look at this for a second. The change in PV is P2V2 minus P1V1. Okay, but volume is constant in this isochoric process. V2 is equal to V1. So wouldn't that be then equal to just the volume times P2 minus P1? That's true. And so it's equal to V delta P. So if I know the pressure in each case, or I know N and T and V, so I can figure out what pressure is for each of the states, then I can have I can fill this in, V delta P. And so I'm going to go back here and say that delta H then is equal to delta U plus V delta P in this case of an isochoric process. So this could be quite useful because I just got delta U above, that was NCV molar delta T. The volume is the constant volume for the process, and the delta P is P2 minus P1. Another possibility here, I'm just going to go this way, and I know that PV is equal to nRT. So therefore, a change in the PV product is actually equal to a change in the product of nR and T. And so that is equal to N1RT1, nope, sorry, that would be final, minus initial, or N1RT1. Of course, the N is constant and R is constant, and so this is really N times R, T2 minus T1. I'm heating and cooling, so there is going to be a difference in temperature. I'm just going to bring this over where it's brighter. And so that's actually equal to NR delta T. So, you see how I can write it like this? Or, I also have that the change in enthalpy is equal to my internal energy change, which was N CV molar delta T, plus this could also be NR delta T. So depending on what information you know or can determine for the process, these few things are going to change. So, yeah, delta T we can find, delta P we can find, and of course delta V is 0 because it's constant volume. Okay. There's no work, so work was equal to 0. So I think we've covered everything that we might actually be asked for this process. Okay. For now, anyway. Later on, we'll add entropy to this mix. And so there we are. Perfect gas, isochoric heating or cooling.